Hi, Southwoods. Here to talk to you about what kind of real life situations can be modeled with exponential functions and linear functions. First, I'd like to give you a few examples of real life situations that are modeled by exponential as opposed to linear functions. In the first example, a library has 8,000 books. That's the start. Also called the y-intercept, when x equals 0. So at time 0, when x equals 0, we have a y-intercept of 8,000. And we're adding 500 more books per year, which is your constant rate of change. So we're constantly adding 500 books per year. This is clearly linear behavior. It has a slope, which is the constant rate of change. It has the starting point, which is the y-intercept. It has an equation of y equals mx plus b, or y equals 500x plus 8,000. Linear behavior. Second example, same thing. We have a gym where customers must start by paying $50. That's your y-intercept at time 0, when x equals 0. And plus, they constantly are adding $3 each time they use the gym. Constant rate of change, linear function. Y equals mx plus b, or in this case, y equals the rate, the constant rate, 3x, plus the y-intercept, which is 50. Linear function. Now in the third example, we have a bank. And when we look at the story, the bank account starts with $10. So that is the y-intercept at time 0. That's where we start. Every month, the amount in the account is tripled. That is not a constant rate of change. We are not adding the same amount each time. It's not constant. We are multiplying the same amount each time, but multiplying is not a constant rate of change. When you're multiplying to get to the next term, that's exponential behavior. So when we write the equation for that, y equals the starting amount, which is $10, times the base, which is the amount it's multiplying by, 3, to the x power, exponential function. So linear growth is constant. Exponential growth increases at a growing rate. It is not constant. When you look at tables, the first thing you need to do before you figure out what kind of behavior the y's are making is you have to decide whether the x's are equally spaced. If the x's are not equally spaced, we can't really look at what the y's are doing. In this case, the x's are equally spaced because each of the x's are increasing by 1 as they move to the next term. Now we can inspect the y's. The y's are increasing at a constant rate of adding 3 each time. So if the x's are equally spaced and the y's are adding 3 each time, that's linear. That's a constant rate of change. So if that constant rate of change, called the slope, we can write the equation y equals 3x plus the y-intercept, which is where x equals 0. So 3x plus 2. So y equals 3x plus 2 is the equation for that linear function. The next example is exponential. The exponential equation, again, the x's are equally spaced. but the y's are not moving at a constant rate. We're adding 3 the first time, and 6 the second time, and 12 the third time. But there is this pattern of multiplying by 2. So if we're multiplying by 2, when we multiply, that tells us that it's exponential behavior. So the exponential behavior, y, is equal to the starting amount. The starting amount is where x equals 0, so the starting amount is 3, or the y-intercept. And the base is what it's being multiplied by each time to the x power, exponential behavior. In real life, many times populations increase or decrease at an exponential rate. In the first example, the population of Haskins begins in the year 2000 with 4,000 people. There's your y-intercept. The base is less than 1. That means it's declining if the base is less than 1. So our decline rate is 0.96, exponential behavior. Now, in the second example, the town of Gainesville begins declining in the year 2000 also, but they only started out with 3,000 people. Their decline rate was constant. They were losing 30 people per year at a constant rate. So their equation was g of x equals starting population of 3,000, losing 30 people per year. Linear behavior. Now, if we graph these, we can see clearly that the town that had the greater starting population was definitely Haskins, h of x. At the y-intercept, which is the year 2000, Haskins is above Gainesville. Now, at about how many years will it take for the population to be the same? Well, that would be at the point of intersection, or the solution, which would be approximately 9.5 years. They will both have a population of 2,715 people. Now, after that, the town of Haskins dips below the town of Gainesville in population until it starts to level off and intersect again at the second point of intersection, or the second solution. So after that, Haskins is less than Gainesville, but only between, in the domain, 9.5 is less than x is less than the second point of intersection, which occurs at 97.5 years. All right? So again, they will be the same amount at 97.5 years. They'll have about 75 people approximately. Now, will both towns eventually have a 0 population? That's tricky. Yes, Gainesville will. So g of x will equal 0 when x is at 100. So after 100 years, the population of Gainesville will be 0. You can ignore this part of the graph that goes below 0 because, of course, we can't have negative population. H of x will never be at 0 because h of x has an asymptote. That means it gets very close. Whoops, asymptote. At y equals 0. So the asymptote is at y equals 0. It gets very, very close to 0, but never actually gets to 0. So on the next slide, you can try a few problems. There's 2 tables for you. One would be linear, the other would be exponential. Figure out which one. Make sure your x's are equally spaced. And you can check your answers on the last slide.